Hi, everyone. So I'm Osbert Bastani. Today I'm going to be telling you about some of the projects my group is working on in the directions of safe and programmable machine learning. Um, and basically, as you all know, like everyone is interested in incorporating machine learning into their systems now. For example, in robotics to solve things like control and perception tasks, but also in broader domains such as healthcare to aid decision making and legal and financial settings and so on. So what I'm interested in is two sides of this problem. So first, how can we build tools to make it easier for developers to incorporate machine learning systems? But also, like, how do we design techniques to make sure that we can ensure that these systems are safe? And both of these directions are part of broader efforts at Penn. So as part of PL Club, which Stephanie talked about a little bit earlier, about verification for software. So there's a lot of interest in both languages for programming with machine learning, as well as for verifying these systems. And it's also part of in the Precise Center, there's a lot of interest in safe autonomy and safe AI, and how can we leverage automated reasoning to prove formal guarantees about machine learning systems. And all of the projects I'm going to be talking about today are very collaborative and part of these larger efforts. So first, I'm going to talk a bit about the side of safety in machine learning first. And in particular, how do we obtain provable guarantees for deep neural networks? And to me, what this really means is how do we really, because deep neural networks are never going to be 100% accurate. So this really means to me, how do we quantify the uncertainty of neural network predictions in a rigorous way? And our solution, which we're working on, is pack confidence sets. And the basic idea is that rather than predict a single label, we're going to design models that predict sets of labels. And then we can use statistical learning theory to obtain provable guarantees about these predicted sets of labels. So you can actually guarantee that this set contains the true label with high probability if you construct it carefully. And so here are just some examples of how this approach applies to ImageNet. And as you can see, as you move from the left to the right, the the images kind of become more and more ambiguous, and correspondingly, the size of the confidence sets also become larger. And we're also kind of interested in kind of tying this back to safety. So for example, one key problem in safe planning for self-driving cars is that they need to forecast the trajectory of pedestrians and other human drivers that they're sharing the roads with. So one key question is whether we can obtain guarantees on these predictions and then use them to plan in a safe way. And so the other side that we're working on, closely related, is programmable machine learning. So just to go over a few directions on this side, one thing we're working on is synthesizing video trajectory queries. So if you're trying to design some of these self-driving car control algorithms, you often want to be able to look at different examples of how humans behave. So the challenge is that, so you can run an object tracker and get, for example, a bunch of car trajectories from these videos. The challenge is that there's a lot of noise. So querying these trajectories can be challenging. So we have a algorithm that basically synthesizes these queries from a small number of labeled input-output examples. So we run the object tracker to get the car trajectories, and then you might write a query like this one, which looks for cars that make a right turn, and then it would automatically tune the parameters in this query in order to maximize the accuracy. We also have work on programmable reinforcement learning. So if you want to program a robot to do a task and then use reinforcement, you can write a high-level specification for the task. For example, in this example, you might want to reach a sequence of 2 goals while avoiding an obstacle O and also making sure that you don't run out of fuel. We have a system that basically automatically compiles this to a reward function that can be used by a reinforcement learning algorithm to train a policy to achieve this goal. Another direction kind of closely related is programmable generation. So if you want to program a generative model to achieve some kind of goal, what we're working on is representing the structure of the data as programs. For example, in this image of a building facade, you can represent you can capture the 2D repeating pattern as a program. Or similarly in poetry, another domain we looked at, you can capture things like rhyming patterns and whatnot using a program. And then the benefit of this is now the user can modify the underlying program in order to guide the generative process. So if you want to increase the amount of rhyming that's available, you just modify the program and the generative model will automatically adjust the output. So I think I'm running out of time. So if you have any questions for me, feel free to look me up and email me to reach out.